All right, everyone, Mr. Graham here. Today I want to kind of elaborate a little bit on what the concepts that were covered in Professor Dave's videos. Professor Dave had a great introduction to the study of motion and motion graphs for accelerated motion. So I'm going to kind of talk a little bit more about that. I'm going to use this program called Algodo to kind of illustrate some things. And I'm actually going to start by talking about something that Professor Dave doesn't really talk too much about in his videos. And there's a reason for that, because in Professor Dave's videos, he started the motion at the origin, essentially at the 0 meter mark. When the person was running, thinking about lunch and all that stuff, they started at the origin, at the 0 meter mark. You don't always have to start at the 0 meter mark. And to kind of illustrate what I'm talking about here, I'm going to go ahead and draw my X and Y axes. We are only talking about motion in the X direction at this point, but we're also going to talk about, I'm going to briefly mention motion in the Y direction. We will come back to this when we study free fall and projectiles and things like that. But notice as I'm drawing my X and my Y axes here, the object is not starting at the origin. The object doesn't need to start at the origin. If you remember our first video about motion, it had to do with the Voyager spacecraft. Obviously, the Voyager spacecraft start at the Earth, but the origin of our coordinate system for the solar system is typically where the sun is. The sun is pretty much stationary with regard to everything else in the solar system. It's not exactly stationary, it does move a little bit, but we'll talk about that when we study Newton's law of universal gravitation. So what I want to elaborate on here are our position vectors. To indicate the position of an object at any particular time, we use what is called a position vector. And so I'm going to use it, and I'm going to have it point to the center of the object. And if I'm consistent there, then I'm good. So my final position, I'll also reference to the center of the object. Now in on-level and pre-AP physics, we call these position vectors, and in this case, it'll be my initial distance from the origin. So we use a lowercase d with a subscript I, indicating the initial distance from the origin. Distance from the origin in the direction specified is our position vector. It is a vector, that's why I've drawn it as an arrow. Now, if I then have my object move at constant speed, so notice over here, if I look at the y-intercept on my position time graph, it starts at the 4 meter mark. So we didn't start at the origin, we started at the 4 meter mark. And it's traveling at constant velocity, so we do expect the slope of our position time graph to tell us that velocity. It's about 4 meters per second. And over here, 0.5 meters per second, that's the slope. And then on our velocity time graph for constant velocity, we have a horizontal line, just like Professor Dave explained, and just like you learned about when you did your Gizmos labs. So I'm gonna let it go a little farther, and then I'm gonna draw the final position vector. So we'll let it go to about the 10 meter mark, right about there. And so now I'm gonna draw my final position vector. My final position vector, it will be measured from the origin still, and it is a vector that points from the origin to the current location of the object. And I'll label that as my final position, or final distance from the origin, d with a subscript f. Now to know the displacement itself is a different vector. So I'll go ahead and put it in red here to make it stand out a little bit. My displacement vector points from where I started, oops, want that to be an arrow, points from where I started to where I ended up. That will be my displacement vector. And my displacement, you might be used to this notation from your math class, it's actually delta d, okay? So that'll be my displacement vector. And yes, delta means what it means whenever you're calculating slope in math class, delta y over delta x. If you guys remember, delta y over delta x, that slope from your math class, that is final y coordinate minus initial y coordinate over final x coordinate minus initial x coordinate. Delta d is the same thing. It just means final position, d, final, minus initial position, d, initial, obviously. And so I would write that like this, d final minus d initial. So I ended up at the 10 meter mark. I started at the 4 meter mark. So delta d has a length or a magnitude of 6 meters, and it's pointing to the right because that's the direction that the object is moving. So that's how we label positions in our motion graphs. That's how we label displacements on our motion graphs, or just to describe an object's motion. All right, so hopefully we got a feel for that now. What I'm gonna do now is start talking about the graphs as they relate to accelerated motion. So I'm gonna go ahead and erase everything on the screen here. Just so you guys know, I'm no good at editing videos. I don't really know how to edit. I'm learning how to teach online, so you're gonna have to put up with my uhs and my ums and the mess ups, so just bear with me when it comes to that. I do apologize. Hopefully that's something that I'll learn how to do better here in the future. So what I got here, again, I got a box, no friction, so it's gonna slide at constant velocity, which we already saw. When I hit play, it just slides at constant velocity. Then these two thrusters I can turn on and off. And when I turn those thrusters on and off, they will cause accelerations. And you'll see those vectors labeled. This is what we call uniformly accelerated motion, or UAM. And that just means it has a constant acceleration. So the thrusters aren't gonna change with their output, their strength. They're not gonna change. And as you'll see, I'm gonna turn on the thruster on the left and it provides this acceleration, this constant acceleration. I'm gonna slow time down a little bit so it doesn't go too fast and get away from me. So the acceleration vector is not changing sides, but notice it is causing my velocity vector to increase. And notice on my velocity time graph, the object's velocity is increasing. It just passed 1.1 meter per second. It started at 0.5. So as the thruster is causing the acceleration, the velocity is increasing. And if you look at the position time graph, again, it was linear at first because it was traveling at constant velocity, but as soon as I hit the thruster, it starts speeding up. Notice that line that is tangent to the curve. That just means it's a straight line that touches the curve at one spot. That's the velocity at that instant, right? That dy over dx little symbol there tells us our velocity at that point. And as I go along the curve, that velocity is getting bigger and bigger, okay? And so notice that the acceleration and the velocity vector are both pointing in the same direction. So it is increasing its velocity, all right? Now, when I turn it off, when I turn that thruster off, now it's not accelerating anymore, and now my velocity is again constant. This is Newton's first law. An object will continue in straight line, constant speed motion unless there's a force acting. There's no force acting now. And so on the position time graph, it is now a straight line. It is now linear. And on my velocity versus time graph, it is now, he's leaving the screen. It is now a horizontal line because it's traveling at constant speed. Now what I'm gonna do is turn on this thruster on the right. And when I turn on that thruster on the right, watch what starts to happen. The acceleration vector now points in the opposite direction. This is like going forward in your car but hitting the brakes. The brakes create a force that points backward, creates an acceleration that points backward, and then you slow down. My velocity vector is, let me speed up time a little bit so you can see it. My velocity vector is decreasing in size, so it is slowing down. I can see from my velocity versus time graph, as time goes on, the velocity is decreasing. The slope on my position time graph is decreasing, okay? And then eventually, the object will come to a stop. The velocity vector will have zero size. And let's look at our graphs when that happens. When it gets to zero size, it's right about here. Now my velocity is zero, right? This is 0 meter per second velocity. It's come to rest. On the left side, the slope is essentially zero meters per second. So I can get that velocity, that 0 meter per second velocity from both of these graphs. And then if I continue to let it go, it will start picking up speed in the negative direction. So my velocity vector will start increasing in the negative direction. And I want you to pay attention to what this line looks like now. It's a straight line going down. I was traveling in the positive direction on this interval. And then I was slowing down though. I was going from a high velocity to a low velocity, and then I stop, and then I start picking up speed in the opposite direction. Just like the slope on position time is velocity, the slope on a velocity time graph is acceleration. So even though I was traveling in the positive direction here in quadrant 1, in quadrant 4, I'm traveling in the negative direction, but that entire time I had a constant acceleration. And notice on the position versus time graph, I have a very nice parabola. That is the type of equation that describes uniformly accelerated motion on a position time graph or distance time graph. That is that is a parabola. It's a quadratic. So a lot of times in your math class, you wonder, why do you learn this stuff? Well, from a physics point of view, you learn how to deal with quadratics so you can study uniformly accelerated motion. Okay. Now notice that it's speeding up, but my velocity time graph is going down into the negative quadrant. it's speeding up. It started at 0 meters per second, then it was at -1 meter per second. If I let it keep going, it'll eventually reach -2 meters per second. So it's speeding up in the negative direction. Now, let me backtrack a little bit and just elaborate on a few things. If the velocity and the acceleration, regardless of what direction they point, if they point in the same direction, the object speeds up. Okay, the object here is speeding up. The velocity is increasing. I can tell that here on this graph, the velocity is increasing. And then if I then turn on the other thruster, then the velocity starts to decrease. So anytime the acceleration vector and velocity vector point in opposite directions, the object will slow down. When they point in the same direction, the object speeds up. So as soon as the velocity vector reverses direction, the object starts speeding up in the opposite direction. Sorry, it's going a little slow now. We'll speed it up a little more. As soon as that happens, now it starts speeding up. Now the acceleration, the acceleration and the velocity vector point in the same direction. So the object is now speeding up, only it's speeding up in the negative direction. That's why my slope is getting steeper here on my position time graph, but it's getting steeper in the negative direction. Therefore, it's traveling with negative velocity. So hopefully that kind of clears up some stuff here. I also want to point something else out, but for on-level and pre-AP, you can kind of stop it here. The rest of the video, I'm going to be referencing some notation that's only for AP Physics 1 and AP Physics C, but they already know this stuff. So if you're pre-AP and on-level, you can check out now and watch the next video. But if you are in, sorry, you gotta bear with me, guys. Sorry about that. If you're in, oh my gosh, I don't know what I'm doing now. If you're in AP Physics 1, stick around. I'm gonna talk about a few things here. Okay, so turn off that. All right. So if you're in AP Physics 1, I'm gonna go ahead and let this guy go a little bit, and I'm gonna draw my coordinate system again, just like I did before. I'll put my y-axis here. Let's make that black. My y-axis here, and my x-axis here. And let's say we're going to start our motion from right here, from this moment right here. We don't use the D's. In AP Physics 1, we don't use D's for positions. We use the variables that represent the direction that the object is actually moving in. So since this object is moving in the x direction, we use x's to denote the positions. And this is my y-axis, my x-axis. So instead of using the D's, we're going to use vectors and label them with x's. So if we start our study of this object's motion here, actually I think I'll use a darker color, then this will be my initial position. We use an x, but instead of using an initial and a final, an I and an F, we don't use that. We use what's called the not subscript. And I don't mean not as in this, I mean not as in NAUGHT. And that's like 0. It's another way of saying 0. Not is like saying 0. And that is the notation that's most commonly used in big kid physics and then university physics. You're not going to see D's in your calculus-based physics classes in college, the classes that you take to become an engineer or a real scientist. You're going to be seeing these not subscripts. And that just means the position that the object is at time 0. So if we start our study of this motion, we hit our stopwatch when the object is here, we call that x naught. That's going to be the initial position of the object. And then let's say the final position, we stop our study of motion after a certain, got to get rid of this guy. After a certain amount of time, we'll let it go for a little bit. Right there. So that object's position, I will then call just x. So when I label this vector, it's just going to be x. No subscript. No subscript here. I just call that my final position x. And there's a reason for this. The reason is that, yes, this is the final position for now, but the object is going to continue to move. So you can actually think of our position x as a function. If we use function notation, our position in the x direction as a function of time. As we let time progress, the position will change. So if we're interested in where that object is going to be at even a later time than right now, then we can still use X for that time. So here's how we denote positions in AP Physics 1 with not subscripts and just the lack of a subscript for the final. And you'll see we'll do the same thing with velocities as well. Delta V will be, the initial V will be V naught, and the final velocity will just be V. And so our displacement vector, again, it's the final minus the initial. And so it would look like this, and we will label that not delta D, but delta X, okay? And then if we have motion in the vertical direction, we would have Y naught as my initial Y position, Y is my final Y position, and then delta Y would be my displacement in the Y direction, okay? That's about it for this one. Take it easy. See you in the next one.